Good morning, students. Welcome to the class on Palladium catalyzed reactions. We will discuss about Stille coupling in this class. What is Stille coupling? So here the variation is we will use stannanes, organotin compounds, either aryl, alkenyl, alkynyl stannanes with of course alkyl halides triplets. The addition is acid chlorides also. Previously we used to have halides or triplets, but here we can also utilize acid halides. Now in the coupling, this organic functional group, organic moiety from stannane will be transferred and coupled with this alkyl. So this one and this one both will couple. So the transfer of R group in the sense from organostannanes, the R group from tin follows alkynyl. That means triple bond transfers first, then double bond, then aryl, then methyl, then of course normal any alkyl group. It is not to mention, of course it is a stereospecific and a regiospecific reaction. As I said earlier, we don't need to worry about the predicting products in these reagents. Because we are using tin, it is a Stille coupling reaction. Only thing is, what we need to worry in the presence of copper iodide, NMP is a base. Here palladium and carbon is the active catalyst. It is 0.5 more percent. Yeah, you can predict the product. Only thing we need to worry is the poisonous nature of tin. It is the only thing we need to worry about the Stille coupling. So the product is coupling between these two moieties. Again, I will mark the functional moieties which must be eliminated. Here halogen, and in this tin, these two must be eliminated, removed, and we can couple the remaining parts. I'll give you some more problems. What is the product here? What is the product here? It can tolerate many functional groups. OTBS is there, alcohol is there. It can tolerate many functional groups. So the product is just couple this carbon and this carbon. Just couple these two things. What is the product here? As I said in the previous examples, instead of alkyl halides, use of triplates is more advantageous as we can easily prepare them. Not only that, we can have both the kinetic control as well as thermodynamic control with carbonyls. In this case, LDA is a kinetic control base. What we will get is we will get anion here that will generate enolate, then enolate ion will be triflated. So this is a kinetic control product. Then we can go for coupling. Since palladium coupling reactions can tolerate many functional groups, even it can also tolerate silicon. What is the product? Now we can also go for thermodynamic control. This is thermodynamic control product. So it generates thermodynamical triplet. Then we can go for coupling. What is the product? I'll just give two more examples for Stille coupling. We can also go for carbonylation. So not only just coupling between these two, we can also go for carbonylation. So carbonyl will come between these two things. Then we will have carbonyl. Here it is an E double bond, so it must be retained. Here also it is E double bond, it must be retained. So this is the product. We can go for carbonylation. This is kinetic control triplet. 2-methyl cyclohexanone. When it is treated with LDA and triflic anhydride, it generates this product. Now, what is the product here? This is also carbonylation. So I will just mark the moieties which must be removed. So this O triplet and tin must be removed, and in between these two carbonyl will come. Similarly, we can also discuss Sonogashira coupling. In Sonogashira coupling, we use copper reagents. Initially, it was developed by Castro Stephens. So it is Castro Stephens coupling, but this alkynyl copper reagent, it is more dangerous, it is explosive. So later Sonogashira modified this Castro Stephens coupling with milder reaction conditions. Because it is explosive, we cannot use them. So the modification of Castro Stephens by Sonogashira is now what is called Sonogashira coupling. In this case, again we can have aromatic halides or tripletes, and they are coupled with alkynes. They are coupled with alkynes in presence of copper. In presence of copper. So this is what is called Sonogashira coupling. You just, it is an example for CH activation. So copper will be induced here, that will undergo coupling in the presence of palladium. This is the product. What is Sonogashira coupling? Coupling of alkynyl or aryl halides or triplets with alkynes, terminal alkynes, in the presence of palladium and copper. So Sonogashira is basically organo-copper reagents. What is the product here? I'll also mark the removing groups. So here hydrogen will be removed, here O triplet will be removed, both of them will be coupled. Just take these two practice problems for Sonogashira coupling. What is Glaser coupling? It is a dimerization, or what we can say homocoupling between two alkynes. Homocoupling, a dimerization of two alkynes, terminal alkynes, in the presence of copper chloride or copper acetate under oxidative conditions. That means we also use air, oxygen for oxidation. So under oxidative coupling, terminal alkynes will be coupled with each other. So here what we prepare 1,3 diines. We prepare 1,3 diines. So this terminal alkyne will be coupled and palladium 0. So the product is, here it generates alkynyl radical. Alkynyl radical. Atmospheric oxygen or oxygen gas is used for as an oxidant. It is used as an oxidant. It generates radicals. So this proton will be abstracted. So alkynyl radical will be generated. That will undergo dimerization. Alkynyl radical will undergo dimerization. So this side we have this functional group, then it will couple with one more alkyne. So it will undergo dimerization to give this product. So here we are generating 1,3 diines. So this is what is called Glaser coupling. This is another variation in Glaser coupling. It is cross coupling between this alkyne and this alkyne, which we also call it as cadiot Chotki-Witch coupling. So it is a cross coupling. It is a cross coupling. Please take this correction. We don't use any palladium here. Glaser coupling is purely done with copper only. So we don't use any palladium here. Take these two practice problems. Here radical will be generated here. So remove this silicon, copper insertion will take place, then it will undergo dimerization. This is the product here. This is acetol. Aldehyde is protected as acetol. this is not purely Glaser coupling. Then it will undergo coupling. So the hydrogen and one of the chlorine, both of them will undergo coupling. Cl. Then it is treated with tetra n-butyl ammonium fluoride THF. Then it has generated triple bond. So this is a slight variation in Glaser coupling, where we have generated 1,3 diene, but through coupling with the palladium, then followed by dehydrohallucination. So under this condition, hydrogen from here, chlorine from here, it is undergoing dehydrohallucination, so that we are generating 1,3 dienes.